I'm just going to recap where we'd got to. You did a couple of mini investigations last week that lead you into the assignment, where you were looking at the effect of concentration on rate and temperature, and that was using the sodium thiosulfate and hydrochloric acid reaction that you're going to use in a more precise way. And that was what I was showing you on this board, how you were going to set the tubes up. Actually, I should have had equal volumes in the two tubes there, but never mind that. Let's just go back to where we'd got to with this. We were recapping the factors that affect rate, bearing in mind that they're usually related in some way to collision theory, and we've talked about concentration and temperature. And this idea about collision theory, that you have to get your particles colliding in the correct orientation, and they've got to have enough energy to break the bonds in the reactants to start with. That's getting over the activation energy. So activation energy is quite important. And I introduced the Maxwell-Boltzmann distribution representing the energy that particles have. And this illustrates the situation in a gas, which obviously we're not using, but it's the, it's the nearest applicable sort of bit of theory to explain the effect, particularly of temperature and catalysts. So the distribution of particles against the energy that they've got has got this sort of what would be like a normal distribution, but one-tailed, so that you've got to get your particles to the point of having enough energy to reach this activation energy point over on the right hand side here before they'll react. And there are the factors that we're going to look at in terms of temperature and catalysts will have an impact on that. And I think that blue dotted line I've drawn on there was showing what a catalyst does. And this was the overview of the actual reaction that you're going to be using, that you used last week. So you're looking at the thiosulfate ions and the hydrogen ions reacting. The sodium and the chloride, they don't actually take part very much. They're sodium ions just stay as sodium ions, chloride ions just stay as chloride ions, whereas there are changes in the other parts. So we can just write out the S2O3 2- aqueous and the 2H plus aqueous will give us, and then it's this sulfur over on the right hand side that's the key, and we have to use a sort of estimate of initial rate of reaction by saying that it's when enough sulfur has formed to obscure well, you had a cross on a piece of paper last week, you're going to have a dot on a piece of paper behind a tube this week. And that is a near enough estimate. And because that will be the same every time, that's okay. Using the same concentrations and the same endpoint and things like that is actually a real convenience thing. It means that you can express rate as 1 over time. It also means, because you can't measure the amount of sulfur that's formed, you can just use 1 over time. You can also make an assumption when we get onto the Arrhenius equation as well, because when we're not using wide ranges of temperatures and we're using the same reaction, you can pretty much take out one of the components of the equation, which is useful. We also get sulfur dioxide, the gas produced. Now, we're not doing it in such large quantities this week as you were last week, so we don't actually need the disposal bath for that to stop the reaction. It can just go down the sink in the fume cupboard. They seem to be just running constantly. So the sulfur dioxide, you won't, because it's only going to be in a boiling tube, it's not the large quantities. Last week you used 50 centimetre cubed, I think. This week it's just going to be 10 of each mixed together. And once you finish with that, it can go down the sink. So your reaction there, you looked at in terms of the concentration and in terms of temperature across a small range, didn't you? And you found it's quite difficult to get the temperature to to cooperate with you, but yeah, that'll get even harder as we go on. We then had a look at it in terms of, well, this was looking at temperature in terms of the Maxwell-Boltzmann distribution over there. and looking at the fact that you generally, what you're doing is just increasing the energy of all the particles. So the whole distribution gets shifted to the right, and therefore you get more of the particles in that area, this red shaded bit over there, with at least activation energy, so it increases the rate. I'm going to correct this, because my other solution should be up there. All right, I'm going to try and rub the other bit out, and of course that probably won't work. Oh, it did. Oh, nearly. Oh, never mind. Fill that in. All right, because that's the general principle behind the practical you're going to do, and it'll just save me drawing it out again. Now, I've given you this handout about rate constants and the Arrhenius equation, so that I don't wander off and get in a mess with this, because it is theoretically quite complicated maths, but actually it's not if you just follow through what's on here. So I'm going to use this. I'm going to hijack Jim Clark's notes and just go through it from here. He starts off this section by reminding us that when you use a rate equation, remember, as he's got there, you know, you've just got your rate equals, and then your rate constant is always this thing. I say it's like a fiddle factor. The rate constant sort of actually absorbs all the things that could change, like temperature, for example, because if you change the temperature, you change the rate constant. And so this actually only applies, it doesn't matter how you write those out particularly, this only applies as long as you're looking at the effect of concentration. All right, so this will be the bit that you use when you're working out, you're going to create a rate equation for the reaction between thiosulfate and hydrochloric acid, and that is all you will need. All right, it is literally just that rate equation. However, this rate constant then, as I said, you know, it's only constant for a given reaction at a given temperature. If you change anything else, if you introduce a catalyst, if you increase the temperature, decrease the temperature, the rate constant changes. So it's no good for actually looking at the effect of temperature. And this is where the Arrhenius equation comes in. So you can see that the notes, the Chem Guide notes are really all you need for this, to be honest. The Arrhenius equation, have I spelt it right? Yes, that's good. The Arrhenius equation's got various bits in it, which Jim Clark very, very clearly defines on here. That's why, you know, I would refer to this, because it's you know, it does just clarify everything that we need. And what we're looking at here then is how other factors have an impact on rate, and how they're having an impact on rate by their effect on the rate constant. So this is going to look at what affects the rate constant, and the rate constant can be defined as, we've then got this rather elaborate equation here. A is going to disappear from a lot of these the calculations, because A, it's known as the pre-exponential factor, and it's if you're just doing the same reaction over and over again, and you're not looking at a wide range of temperatures, it's pretty much constant, so it can actually be discounted, which makes life a lot easier. I'll give you a proper description in a minute, or we'll use the Chem Guide description. And that's multiplied by E, and that's the mathematical quantity 2 point whatever it is, 2.8 something or other, yeah? Which, yeah, you'll be coming across all over the place. And that is to the power of minus the activation energy, and of course that particularly is affected by catalysts, divided by, and then that's the gas constant, which is a constant that we have briefly met before, and temperature. So if we're looking at the impact of catalysts and temperature, this is going to be useful because it tells us how the rate constant varies in an expression that uses the activation energy, which is there. All right, so that's the activation energy. And it also gives us a link to temperature, which is there. Okay, so where our rate equation up here was just about concentration, we've now got an expression that we can play around with to see, you know, what effect changing the activation energy or changing the temperature is. So we're going to work through, we're just going to have a look at what else is on here because there's a couple of good examples to use. Now over the page you've got definitions of all these bits. And I think they just fit nicely onto one side, which is good. All right. Now, the various symbols, and I think I've modified it slightly from the website so it fits nicely here. And I think on the website it said, starting with the easy bits, right? The things that we recognise, perhaps. You've got temperature there. We know what temperature is, and to fit into the equation, it's measured in kelvins. All right, so Kelvin is a unit of the full name with a small k, but the unit, of course, is an uppercase K. All right, so all right, that's in kelvins, not degrees Kelvin, not Kelvin K with a not a small k, but in big K. The gas constant. We haven't got it there, but it's 8 point something or other, which either appears on here or I'll have written it down somewhere else. It's just not one I've got sort of registered in my brain, but we will check that one out. Times 10 to the minus 5 or something? 8.31. Oh, I suppose it depends on your units. Okay. The gas constant then. 8.31 joules, just joules, per Kelvin per mole. Yeah, I'm probably thinking in kilojoules or something. All right, so remember that one's in joules. And this, you've got to be really careful here, haven't you? Joules, kilojoules. Right. Now, the activation energy, up at the top there, it is the minimum energy for the reaction to occur then. And again, to fit it into the equation, it's expressed in joules per mole, not kilojoules per mole. All right, so that's joules per mole. So we've got to keep all our units in line with each other, size-wise, yeah? If you need to at any point, of course you can convert, but do it at the end, you know, if you want to convert from joules to kilojoules or whatever, but don't do it on the way. You do need to make sure that you're being consistent throughout here. I think that's just about, yeah, that's got the important bits in there. Now, E then has got this standard value, 2.718 and some other bits. Doesn't really matter. I love the way he describes it on here. You don't need to worry exactly what it means. If you've got to do calculations, you might have to find it on your calculator. So it's e to the x, and it's be the same key as the ln, natural logarithm, which is sometimes pronounced line or lin. Okay, so it's the inverse of it, if you like. So we will need those. Don't worry about them yet. And then you've got the expression, and then that's really badly written there, but it's e to the minus EA over RT, and the A has dropped out there, hasn't it? All right, so that expression is this whole thing. All right, now that is a really useful part of the expression. And yeah, for reasons that are beyond the scope of any course at this level, that includes us quite neatly, because I wouldn't want to have to try and explain it. This expression counts the fraction of the molecules present in a gas, or we're just assuming anything else. But it's one of those assumptions that it's worth just mentioning sometimes, which have energies equal to or in excess of activation energy at a particular temperature. Okay, so it's the fraction of molecules. Now, in terms of a fraction, you tend to think, oh, that's one number over another. It doesn't really come out like that, but it's a number that we can compare with another number. And what we're looking for is, if we calculate that at, let's say, 20 degrees C, oh, shouldn't have done, should I? 293 kelvins. And if we then calculate it again, 10 degrees or 10 kelvins higher, the number should double. Yeah, it's one of those things that we said, that for 10 degrees rise in temperature, a rate of reaction will approximately double. And so what we should be finding is that the number of particles with enough energy to react should be twice as many at the higher temperature. And you will be able to do that from your temperature investigation. But it will mean you've got to do some tricky maths on that to actually rearrange it. All right, we're going to be taking logarithms and all sorts with this, but that's all right. Jim Clark will help us. And then you've got at the bottom this thing called the frequency factor, or pre-exponential factor, or steric factor. This includes things like frequency of collisions and their orientation varies slightly with temperature, not much. So it's often taken as constant across small temperature ranges. So essentially, if we're comparing two temperatures, we can take that out. We don't need it, which is convenient. Okay, if we look at the next side, I love the way he does this. By this time, you've probably forgotten what the original Arrhenius equation looked like. Here it is again. And it is just how your brain works, isn't it? You know, you've worked through all that, and then if you want to say something else about it, you actually need to revisit your starting point. So it's a good approach. Anybody would think, you know, he's got years and years of experience teaching. So we've got our K equals A, E to the minus EA over RT. You can then rearrange this using logarithms. So it's not rearranging it, but you can write it this way. Now, I know you've done some work on logarithms. Does that next line make sense? If you take natural logarithms of both sides, you're not saying no, which I'm assuming means you've sort of done this, but you've forgotten how. Yeah? Yes. Right, okay. Well, if you take logarithms of both sides, you retain the equality. It's like you do the same thing to both sides. It's basic algebra. So, you know, if you've got x equals y, when the log of x will equal the log of y. Yeah? So if you take logarithms of both sides, you're not changing the inequality in any way. Sorry, equality. Not changing the equality. So you might wonder why this is useful. Well, it gets that power, that exponential, you know, the what you call it, that bit up at the top. But it brings it down if you do, if you take logarithms. And if we take the rules, like the rules of indices, that was it, isn't it? You know, rules of indices and what you do with them if you multiply them or take logarithms of them and all that sort of thing. If you take the natural log of E, what do you get? You'll get 1. Yeah, because it's the power to which you raise E. All right, powers and logs are like the reverse of each other. The natural log of E will be 1. Check it. I hope it is. I hope I'm making enough sense of that. And then if you take a logarithm of a power, it brings it down to the real world, if you like. Okay? And that is now actually in a usable form. You can do something with that, particularly if we're going to get rid of the natural log of A. All right, you might need to revisit work on logarithms and indices, but the reason the course is arranged as it is so that you're supposed to have done a bit on that, so this is not too mysterious by the time you get here. A quick recap might be in order, because I think you've gone on to calculus now, haven't you? Differentiation and integration. So you'll have forgotten what you did. So never mind, natural logs are just to the base e, all right? Which means it's as though you are counting in multiples of e. If you were to take a logarithm to base 10, did you do logarithms to base 10? There's always your starting point. It's as though you're saying 10 to the power of something, and I've done this several times. If we say 10 to the power 2 is 100, the log to base 10 of 100 is 2. So it's the power to which you raise the base to get your number. Yeah? So you apply that in the same way, where ln is a logarithm to base e. You could write it log e, but we don't. The standard is to write it with an n. So if we were to do, 10 to the power 1 is 10. So if we did log 10 of 10 is 1. Now let me see if I can make this work. There is always a risk I won't, of course. So if we do that to the power 1, no, I'm doing silly things now. Right. E to the power, whoa, I went the wrong way round. Let's try that again. E to the 1 will be E. So log, in other words, log, well, it would be right liking it like that, which we don't, of the number on that side is the power we raised it to get it there. Is that making some sense, that logarithms are this inverse of the index? Yeah? Good. You don't really have to know why and all that. Just use the forms of the equations that I give you. I'll give you quite a tricky one for doing the activation energy, which you need to use in the form that it's on the assignment. I know you can look it up and get other ways of doing it, but I would stick with the way I give you. Right, so if we backtrack to this, all right, we can use that now, all right, so we can actually make something out of this. So if we go on to Jim's next bit, using the Arrhenius equation, looking at the effect of a change of temperature, and this is what the second part of your assignment, or the second part of the practical work, will be. So you can use it to show the effect of change of temperature on the rate constant, and therefore on the rate of the reaction, because that is determined by the constant. So if the rate constant doubles, for example, so will the rate of reaction. All right, remind yourself by looking at that. No, that. Right, you double K, you're going to double the rate. So the example that he gives here, what happens if you increase the temperature by 10 degrees C, say from 20 to 30 degrees C, or 293 to 303 kelvins. Now this is where it becomes useful to say that the frequency factor is approximately constant for such a small temperature change, and so we can sort of ignore it. So what we've got to look at is how that expression there, which is, it's seriously messy the way it comes out. I don't know if it's better on the website, but once it's copied in, it is this expression. He's got it, in brackets really. That is how it should look, but it really isn't. Doesn't matter where the minus is, as long as it's coming out. Well, sometimes you see it written at the top, but yeah, that's what that's supposed to look like. Anyway, what we want to do is look how that changes with different temperatures. Now, what you're going to have, of course, is T here. We're going to have 2 different values for it. So we're going to have, for one of the readings. We're going to have 293, and then for the other one we've got 303. So we're going to calculate this twice, is where we go with this, to look at the different fractions of molecules with energies equal to or in excess of activation energy. So if you go over the page, you'll see it worked through. Now, you have to have an activation energy value for doing it like this, but you can work out the activation energy. You will be able to from this. Honestly, it is possible. So if we assumed an activation energy of 50 kilojoules per mole, remember we've got to work in joules, so we're going to have to convert that. So in the equation, that's got to be 50,000 joules per mole. We've got a value for the gas constant there, 8.31 joules per Kelvin per mole. We've then got the two calculations for the two different temperatures. So for the first one, it comes out, if you feed in all those numbers, e to the minus, then on the top you've got the activation energy of 50,000. On the bottom you've got the 8.31 times the temperature, 293, and it comes out at 1.21 times 10 to the minus 9. If you then increase the temperature by 10 kelvins, all you're doing is putting in a different number in the index there. So you still get 50,000, you've still got your 8.31, but now you've got times 303, and it comes out at 2.38 times 10 to the minus 9. Well, what do you know? It's almost exactly double, doesn't it? So, you know, this is the fraction of particles that have energy equal to or in excess of the activation energy. So if there's twice as many of those, you could expect twice as many collisions, you could expect the rate to double. It won't quite, never does. But that is something that you can then work out. All right, so fingers crossed it will come out. Usually comes out okay. Right. Does make the point further down, this actually only works for reactions that have got activation energies about 50 kilojoules per mole, about room temperature. Yes, if you're at other temperatures, you get all sorts of other results, but you know, we sort of work within normal ranges most of the time. Right, now you don't need that bit straight away, but now I'm going to get you started on the practical work for this. And so we need to go back to having a look at the, no, it wasn't on there, was it? There we are, the setup for the equipment. Now, I don't know whether, I'll give you the assignment out in a minute when I've explained it first. You're going to be given you've got the two solutions, you've got hydrochloric acid and you've got sodium thiosulfate. Now these are very carefully in two different sized bottles. Sodium thiosulfate is in the smaller bottle and it is at a concentration of 0.1 moles per decimeter cubed. All right. The hydrochloric acid is in the larger bottle at a concentration of 0.5 moles per decimeter cubed. Let's keep track of this. So that and that okay. The first thing you're going to do is to look at the effect of changing the concentration of the thiosulfate. And I would suggest using 5 different concentrations. Now you're starting at 0.1. So I would suggest that your concentrations could be 0.08, 0.06, 0.04, 0.02, and the 0.1. All right, from that, you've just got to work out the dilutions for that, haven't you? Okay, might need to work together to work that out. And you keep the concentration of the hydrochloric acid constant. Remember, this is how you're going to work out the order of reaction with respect to the thiosulfate. Now you actually know what it is from what you did last week. All right, you then keep the thiosulfate constant, and you do some different concentrations of the hydrochloric acid. I wouldn't bother doing very many concentrations with this, shall I say. All right, you got 0.5 there. If you also did 0.3 and 0.1, you'd probably realise what was happening. Okay, so that is altogether 8 different practicals, 8 different measures you've got to do. 5 changing the thiosulfate concentration, 3 changing the hydrochloric acid concentration. So you're looking at the effective concentration there. You can then plot graphs, work out the order of reaction with respect to thiosulfate, work out the order of reaction with respect to the hydrochloric acid. You can then draft a rate equation. Now, you will also be able to work out the rate constant. We'll come back to that. All right, the instructions are in the assignment, don't worry. Once you've got that, you then have a second part where you can look at the effect of temperature. Well, you might as well use the concentrations that they come at, and you have to set up different temperatures. Now, this is where it gets tricky. I mean, you know last week how awkward it was trying to hit specific temperatures, but the results did come out okay. Now, the piece of the assignment that I'm giving you is only the first part. All right, I haven't attached the other bit to it. The other part, section 2, part 2, comes separately once we've done the equilibrium bit. But you've got part 1 that covers the whole of assessment criteria 2.1, 2.3, 2.1, 2 and 3 coming out, and then part 2 covering 4 and 5 will, that's a separate bit. But it takes you through what you need to record. It doesn't take you through the actual practical details. So I'll just redraw that diagram actually. You're going to use boiling tubes and 10 centimetre cubed of each solution. All right. So what I started describing, which I didn't finish, is that the hydrochloric acid is in a big bottle, the thiosulfate is in a small bottle. What you must be very careful of is not to cross-contaminate them as you're measuring them. So we have 2 different sized measuring cylinders for you. Hydrochloric acid in the big bottle, use the big measuring cylinder for 10 centimetre cubed of that. And the thiosulfate in the smaller bottle, use the small measuring cylinder. All right. Now, you can pour into the bigger one from the bottle without too much difficulty, I'd have thought, although I will get some little teat pipettes out for you, just to be sure. Pouring into these little ones can be tricky, so you have got a small beaker to help with that. All right. The other beaker that you've got is your water bath. Now, the reason for this is to maintain as constant a temperature as possible. Now, you're not going to get on to temperature today, but of course, we're going to do this tomorrow as well, and then next Tuesday afternoon is put aside for it as well. And if you still haven't finished at that point, then I think next Thursday morning study skills can probably be used to, to finish off any extra bits. Because you do find sometimes that, you've taken some readings, you perhaps do a sketch graph to see how it's going, and you find that one of your points is way out and you need to repeat it. Most years I have people coming back just to repeat 1 or 2 readings on this, so that's why I've put plenty of time aside for it. Right, let's just go back to the diagram of how this is set up. In order then to keep your reaction at a fairly constant temperature, and just to practice the setup as well, of course, for when you're doing temperature, then I would suggest just start setting it up in the way that we've got in that diagram. Your 2 tubes, one of them, this will be your reaction tube, held in a clamp stand. in a beaker of water to maintain a constant temperature. Thermometer in there so that you can record that constant temperature and you can put it into your write-up. Now, one of the things with this I would suggest is that you're going to want to describe how your equipment is set up. Drawing it these days is, you know, just not worth the bother. You might as well take a photograph of it and you can put that into your work. All right, you can photograph your equipment setup and, you know, it just makes it clear what you're doing. And then stand that on a tripod and a gauze. Oh, yeah, that would fall over, wouldn't it? That, you know, just you might get onto the temperature one this afternoon. Never know. I doubt it. You then, with your this takes quite a bit of doing actually. You have to fix a little strip of paper on the beaker behind your reaction tube, and it just needs a nice sort of intense black dot on it. So don't make it too big, don't make it cover the whole beaker. We've got bits of paper, we've got black markers, we've got sellotape. And you have your 10 centimetre cubed. I'm not sure where that will come up to in one of these. I don't think it comes that far up, but I'll put it there just for whatever. And I would just be consistent about which one you tip into which, I think. I'd probably put the thiosulfate in here. And the acid in there. Just give them a while to sort of reach a temperature. I think the temperature will be all right, actually, because they've not been in the fridge, these ones. If you just give them a couple of minutes to make sure they, you know, are stable temperature. And then you pour your acid into your thiosulfate, start timing, record the time it takes for your dot to disappear. Then take that, tip it down the sink in the fume cupboard, rinse them out and start again. All right, they only need rinsing under the tap. All right, so take them over to the side, give them a rinse and you can start again. Although actually, if we're, yeah, just give them a good shake to get the water out, because otherwise you will be having an impact on the concentration, won't you? Right, we've got quite a lot of boiling tubes, but not enough to do, because if you've got to do 8, you know, that's a lot of boiling tubes. All right. So you do different concentrations of thiosulfate with the same concentration of acid, and then you do different concentrations of acid with the same concentration of thiosulfate. But, you know, like I say, don't have to rush through it because you've got plenty of time tomorrow. Tomorrow afternoon, that is literally all that's planned. You just come in and get on with it, really. The trolley will just be here. All right, so I'll stop the recording at that point and give you the instructions.